Good morning, everybody. My name is Ulises Nunez, and I am a PhD student at Georgia Tech under the supervision of Dr. Glenn Lightsey at the Space Systems Design Lab. And today, it is a huge honor to present to you on the topic relating collision probability and missed distance indicators in spacecraft formation collision risk analysis. We will start this discussion by motivating this work. Spacecraft formation flying is a set of more than one spacecraft that track dynamic states relative to one another. Having such an arrangement of spacecraft is beneficial because it can endow missions with improved scalability and maintainability. It also has many potential scientific applications, such as gravity field recovery, weather forecasting, exoplanet detection, and more. Collision avoidance is a necessity in formation flight because of kinetic threats to any formation, both from external debris and among agents in such formations, due to drifting or maneuvering. These threats are constant, therefore, safety concerns must be balanced with wise propellant usage. Work in collision avoidance in formation flight can be broadly categorized into passive and active schemes. Passive schemes focus on the design of passively safe relative orbits, with maneuvers only indirectly addressing collision risk. Active schemes focus on monitoring collision risk, checking safety criteria violation, and, where needed, planning and execution of dedicated collision avoidance maneuvers. This work focuses on active collision avoidance methods, which are characterized by their collision risk indicators. In these charts, you see conceptual illustrations of probability density functions, or PDFs, of the relative position between two agents. One type of collision risk indicator is missed distance, which is any statistical description of the physical separation between two agents, as seen on the left. The other type of collision risk indicator is the probability of collision, which is the probability mass of the relative position which is inside of a collision region. Collision risk is mitigated by setting constraints in an optimal control problem in terms of these indicators. The main intention of this work is to check if collision risk assessments based on missed distance and collision probability are consistent. In other words, we would like to understand whether or not conclusions drawn from one class of collision risk indicator hold when examining the other class of indicator. Investigating this question has many benefits. First, if both indicators are used, then understanding the relationship between them can help give a more complete representation of collision risk. Second, if only one indicator is used, then understanding the relationship between both indicators can help understand what trade-offs there are in choosing one indicator over the other, as well as understanding whether or not they can be used interchangeably. Overall, understanding the relationship between missed distance and probability of collision is a step toward bridging the different philosophies of active collision avoidance methods. Without further ado, let's dive right in. First, we will discuss the idea of a characteristic length or hard body radius for some agent I, denoted by Li, which we define here to be the furthest Euclidean distance from its center of mass to any point in its body, preferably under a worst-case configuration of all appendages and deployables. Then we make the hard body radius assumption, which simply holds that the body of agent I can be approximated by a ball with radius Li centered at the center of mass. This is a conservative assumption that also simplifies the definition of collision events. It should be noted that these balls are surrogates for the size of the object, and they are not position PDFs. With these notions, we define a collision event as the condition when distinct agents occupy portions of the same volume of space at the same time. That is, when their circumscribing balls have a non-empty intersection. Alternatively, a collision occurs when the distance between centers of mass is less than the sum of their hard body radii. Now, we will delve into defining probabilities of collision. We will assume continuous relative position PDFs for this discussion. The grid contour you see represents a three-dimensional relative position PDF. Although only a contour is shown, such PDFs are generally defined in the entire three-dimensional Euclidean space. The red region is the true collision region, meaning that a collision event, as defined in the previous slide, occurs when the relative position between agents is in that region. Therefore, The kinematic probability of collision, or KPC, is the probability mass of the relative position PDF that is inside the collision region. The plane with gray grid is called a projection plane. It is called that because the relative position PDF can be projected onto that plane, and the three-dimensional collision ball can be projected onto a two-dimensional disk in that plane. We can then define the projection KPC as the probability mass of the projected relative position PDF inside the projected collision disk. The reason for making this distinction between true and projection KPCs is that before we compare missed distance and collision probability waveforms, it is important to understand if it makes sense to characterize collision risk as approximated by a projection KPC. In the literature, several authors conceptualize collision risk as measured by a projection KPC, such as in the radial along-track plane or in a plane normal to the expected relative position rate. Therefore, it is important to know whether such approximations are adequate. The main theoretical result presented in the paper is that every projection KPC is an overestimate of the corresponding true KPC, and this holds regardless of projection plane choice. Furthermore, if the relative position PDF is positively valued in its entire domain, then the overestimate is strict, meaning that in those cases, the difference between projection KPCs and true KPCs is not trivial. This result is general in that it is instantaneous and it does not depend on the underlying dynamics. It also applies to normally distributed relative states in particular. This result is significant because it implies that using projection KPCs as safety constraint satisfaction criteria leads to probabilistic false positives when compared to using true KPC constraints. Therefore, using projection KPCs results in more actions than warranted with risk thresholds expressed in terms of true KPCs, which, in the long run, translates to reduced mission lifetime. Naturally, such a significant result should be validated through simulation. Here, this is done through a Monte Carlo simulation for relative dynamic states subject to Clohessy-Wilshire or CW dynamics that have normal prior distribution. Each case considered has 320 million particles in the sample. The reason for such large samples is that KPCs as low as 1 in 10 million are considered significant. This requirement is adopted from the practice of the Conjunction Analysis and Risk Assessment Group, or CARA, at NASA Goddard Space Flight Center, who work on debris collision risk assessment. This slide shows representative simulation results that hold for every case considered to some extent. The green waveforms in both charts represent numerically computed projection KPCs. On the left, you see projections onto coordinate planes, that is, the XY, XZ, and YZ planes. On the right, you see projections normal to the relative position and the relative position rate vectors. In both charts, the purple smooth waveform represents the numerically computed true KPC, and the asterisks are the sample KPC results. It is found that the sample KPC converges to the true KPC. Second, it is found that the sample KPC does not converge to any projection KPC. This validates the main theoretical result of the paper. From now on, we'll refer to sample KPCs and true KPCs interchangeably. These representative simulation results will also serve as a transition into the next area of contribution in this presentation. We use the notion of consistency of collision risk assessments to refer to the intuition that whenever two agents have small separation, the probability of collision between the two agents should be high, and when their separation is large, collision probability should be low. However, in this example, it can be seen that collision risk assessments based on the norm of expected relative position are not consistent with KPC-based assessments because, more often than not, further separation coincides with high probability of collision, and closest approach between agents coincides with low probability of collision. It is clear that collision risk assessments based on either risk indicator lead to contradicting conclusions. This notion of consistency will be the subject of the rest of the presentation. Three separation measures are proposed which are hypothesized to produce consistent collision risk assessments when compared to true KPCs. The first proposed separation measure is the minimum distance from the origin to a 3 sigma contour that is geometric in the sense that it is located 3 standard deviations away from the mean of the distribution. This is referred to as methodology 1. It should be noted that for a three-dimensional normal random variable, only 97.07% of cases are within this geometric 3 sigma contour. Naturally, the second proposed separation measure is the minimum distance from the origin to a 3 sigma contour that is equivalent in the sense that 99.73% of relative position cases are within that covariance contour. This coincides with the colloquial understanding of a 3 sigma event. This is referred to as methodology 2. Finally, the third proposed separation measure is the percentile in the empirical distance distribution, so that 99.73% of distances are higher than that. This is referred to as methodology 3. The cases considered encompass a wide variety of closed CW relative orbits, with and without cross-track motion. And out of the cases with cross-track motion, we are considering cases where the radial and cross-track motion are both in and out of phase. The specific values of the initial expected relative state as well as the initial relative covariance are chosen so as to observe significant KPCs over a two-orbit horizon. The first result is to rigorously validate sample KPC convergence to the true KPC. On the left, you see the correlation coefficient between sample and true KPC waveforms, which is the normalized inner product between the two waveforms, and which has values between plus and minus 1. From real analysis, we know that a correlation coefficient of exactly 1 for continuous waveforms implies that both waveforms are equal almost everywhere to within a scaling constant. We see that the correlation coefficient does approximate 1. Since, as we see on the right, the simple KPC L2 norm underestimates the true KPC L2 norm by only 3% at worst, convergence is demonstrated for engineering purposes. The second result is to rigorously validate that simple KPCs do not converge to projection KPCs. This is shown by how the correlation coefficient between sample and projection KPC waveforms does not approximate 1 consistently for any meaningful projection plane choice over a wide variety of closed CW relative orbits. Therefore, the main theoretical result of the paper is rigorously validated in a CW simulation environment. The third and final result is to show which distance measures, together with true KPC, produce consistent collision risk assessments. For the cases of no cross-track motion and with radial and cross-track motion in phase, it can be qualitatively seen that the 99.73% minimum distance waveform indicates closest approach when true KPC indicates highest collision risk, and it indicates largest separation when true KPC indicates lowest collision risk. On the other hand, that does not occur with the minimum distance to either kind of 3 sigma contour. We introduced the collision correlation index, which is the correlation coefficient between the unbiased waveforms of the true KPC and some separation measure. Through this definition, the notion of consistency between collision risk indicators is formalized by stating that the collision correlation index should be negative. More or less, this would imply that agent separation is reduced while collision probability increases, and vice versa, as seen on the chart. Therefore, the more consistent the waveforms are, the closer the collision correlation index should be to -1. This chart is the main simulation result of this paper, and it shows the collision correlation index for the case of radial and cross-track motion being out of phase. This corresponds to the popular eccentricity inclination vector separation scheme for passive formation flight collision avoidance. The cases considered encompass initial phases of radial motion across the spectrum of initial conditions. We can see that the norm of expected relative position, which is a state statistic obtained during filtering, has the correct relationship to true KPC as often as it has the incorrect relationship. In some sense, the norm of expected relative position has no correlation with true KPC. This means that the norm of expected relative position is not an adequate collision risk indicator. Furthermore, it is found that out of the proposed separation measures, the 99.73% minimum distance is the only one that produces consistent collision risk assessments across all cases. This consistency is generally stronger for the 99.73% minimum distance than for other separation measures as indicated by the collision correlation index. In conclusion, we have presented two contributions in this work. First, projection KPCs overestimate true KPCs. This result is stated as a theorem, and it is validated through Monte Carlo simulation in an environment subject to CW dynamics. This result implies that approximating collision risk information flight by a projection KPC is an inadequate practice. Second, it is found that not every separation measure, together with true KPC, produces consistent collision risk assessments. The worst performing separation measure is the norm of expected relative position, and the best performing one is the 99.73% minimum value in the distance distribution. This result helped bridge the gap between distance-based and probability-based collision risk assessments information flight. Thank you all so much for watching this presentation, and I look forward to your questions.